Okay, so what I want to do in this video is derive the constant acceleration equations, also known as kinematic equations, okay? So, we're going to be taking a calculus-based approach with this. So first we have to know what exactly constant acceleration is, and that's just when the constant acceleration function is just equal to a constant a. It does not depend on t or any input that you give it. It will just spit out the same thing over and over. The next thing is that we also need to know its initial velocity, which I'm just going to say it's v naught. The initial velocity is just the initial velocity. And the initial position, I'm going to use s, is just the initial position, right? We don't know, it can represent anything, but it's just an initial position and an initial velocity. So, with this, we know dv over dt is equal to a. And then we can use separation of variables. So dv is equal to a dt. In other words, integral of dv is equal to the integral of a dt, which is v equals at plus c. And now we plug in this first initial condition, we get v naught equals c, right? So you substitute v for v naught, because that's what it's equal to, and you substitute t for 0, or 0 for t. That means we get v equals at plus v naught, or the way I would write it as this. This is our very first equation. This is the first kinematic equation that we will derive. Now let's derive the second one. The second one, we have to use a very similar idea, but now use position. We know that this is equal to v, but from this one we know exactly what v is equal to, right? V is equal to v naught plus at. Now we use separation of variables. ds is equal to v naught plus at times dt. We use integrate, and we get s is equal to v naught t plus half at squared plus c, and then we plug in our initial condition. We get s naught is equal to c, right? You plug in 0 for t, and you plug in s naught for s, and then that means we get s is equal to v naught t plus 1/2 at squared plus s naught. I'm going to rewrite it in this way, which I feel like is the best way to write it. And this is our second one. Not too difficult, because we just use the same process. This was a bigger function. These are the first two. I want to derive the second one, or the third one, sorry. The third one, and the third one uses a different idea. So, what we want to do is, we know dv over dt is equal to a, and we know ds over dt is equal to v. What I want to find is one specific derivative or like differential thingy where we relate, what do we relate? We relate dv to ds, right? This one is velocity to time, this one's position to time. Now what about velocity to position? So what I'm going to do here is take this and multiply by 1, but that 1 will be something kind of interesting. It's going to be dt over dt. And that's just this, you can do that because you're just multiplying this fraction, if you want to think of it, by 1, but this fraction is just kind of special in its own way. So then this is equal to dv over dt times dt over ds, right? We know what this is, and we know what this is. This is 1 over velocity, right? This is the reciprocal. This is acceleration. So then this is a over v. The next step is to take what we know, dv ds equals a over v, and use separation of variables here. So we want to kick all the v stuff to the left and kick all the non-v stuff to the right. So v dv is equal to a ds. Now I want to take a specific definite integral. And the definite integral I want to take is just evaluating the integral from v, or v naught to v, for the function. And then also, I want to take the definite integral from these two positions, right? From the positions, and the reason why I'm doing it, because this is ds, and this is written in dv. So we integrate at this point. Integration with respect to whatever it is, right? So this one's v, so this one's 1/2 v squared, evaluated v naught, and v, and that's equal to as evaluated to the initial position, the final position, and let's just evaluate these. I'm going to bring it over here. So it's 1/2 v squared minus v naught squared is equal to a s minus s naught, right? And now I just want to make this look pretty. The way we do it is by just multiplying 2 on both sides, so it's v squared minus v naught squared equals 2a s minus s naught. And then I would like to just solve for v squared just to make it the form I want it to be. And then I also want to change this to delta s. So this is the third equation. And then now we move on to the last one. The last one will need to take a graphical approach. I feel like this one should be included into the main 3, but some books don't talk about this fourth kinematic equation, and I feel like it should be included as a part of the 3. So this is kind of like the fourth one that no one tells you about, but it still exists. And it goes through this idea of a graphical argument. So what I want to argue here is that we know this will give a constant velocity, right? It can be constant, so it's going to be flat. That means the velocity will be something diagonal, right? Just positive diagonal. It doesn't matter where we start. Right here, we can have started anywhere else, but the main argument here is what I'm trying to say is that if we take 2 points, here and here, and these will be our initial velocity and our final velocity. If we take the average of these two values, right, kind of like with data, when we take the average of data, you have to, or the mean, you want to take the entries and divide it by how many entries there are. What I want to argue is that it is the same as the definition for average velocity. So, in other words, if I were to put it in words, the averages of the velocities is equal to average velocity. And this is basically the fourth one that often gets left behind. It's this one. And this is true. The averages of the velocity does equal average velocity, right? You take the average velocity from here to here, you get somewhere in the middle, which is average velocity. So let me rewrite them all for you. So, good summary. V naught plus at, this was the very first one. Delta s is equal to v naught t plus half at squared. V squared equals v naught squared plus 2a delta s. And then the final one is v final plus v initial over 2 is equal to the average velocity. I'm just going to write it as t. So, these are the kinematic equations. Alright, and I would recommend memorizing them because they're super important, especially in future problems we'll stumble across. We should know these and when to use them. So that's it for this video. I hope this derivation makes sense to you. For people in calculus, it's just a separable differential equation. And that's it. So that's it for this video.